Welcome. This is going to be our first lesson in this geometry course that I created. And essentially, my goal for this course is to go from the really, really basics. Like today, right, in this first lesson, we're going to learn about basic figures, and all the way at some point, we're going to learn about like complex proofs and like multi-step problems with some, abstract algebra involved. But today, our focus is just on lesson 1.1, which is basic geometric figures. So, let's just get started, right? I don't want to waste any of your time. So, start with points, right? Now, a true geometric point has no dimension, right? Now, when we label points on paper, right, that technically does have some dimension to it, right? Because we're drawing on the paper. Um, but in its true form, right, theoretically, a point has no dimension, right? And when we indicate points in geometry, we essentially just represent them with a dot and then label them with a letter, a capital letter. So as you see here, right, like point A, for example, right, we would just put a dot there and then label it as a capital letter A, right? So that's a point. Nothing too complex so far, right? Hopefully. Okay, so now we have a line, right? Now, a line is different from a point because it only has one dimension, right, compared to the zero dimensions that a point has, and it continues forever in both directions, right? So if you want to like connect these two terms together, a point and a line, I think the best way to think about it is that you can think of a line as a series of points, right, that extend in like opposite directions. So like if you look at this line, and I'm going to explain the notation a bit more afterwards, but like if you just look at this specifically, right, this visual here, um, if you think of each specific section as like a point, right, and you basically those stack those points up, um, that's essentially what a line is, right? Uh, and of course, it continues forever in both directions, right? And as far as the notation goes for lines in geometry, um, a common thing you should know is that if there's like 2 points in a line, so for example, here we have points A and B, uh, to show that it's a line, we will use those points as kind of like our, I guess you can say our reference, right, in A and B, and then draw like this specific symbol over it, right, a line with two arrows going in both directions. That's essentially the entire notation for a line, right? And also sometimes, of course, like you have A, B here, but it can also be B, A, right? The order doesn't matter when you're like writing the notation down for a line. Next is line segment. Now, a line segment is different from a line because it's actually kind of a subset, right? So it's a portion of a line that's lying strictly between the 2 points, right? So if you took, for example, let's go to the line that we learned about earlier, and if you looked at this specific section, right, between the 2 points, that is a line segment, right? That is exactly what we have here. And notation wise, right, very similar to a line. Um, we use points A and B as our reference, and again, the order doesn't matter, so we can have A, B, or B, A. The only difference from a line is that instead of drawing like this symbol, right, with the two arrows, you just draw a straight line, right? That's how you denote line segments in geometry, right? And an important thing to know about line segments, right, is their finite length, which means that they don't go forever in one or two directions, right? They're just finite, they have one specific length, and they just stick to it, right? Now, moving on from that, we have rays, right? And again, a ray is a part of a line that begins at some specific point and continues forever in one direction, right? So like I said, it's a part of a line, right? Specifically, if you looked at our line visual here, um, if you look at this specific part, right, that's going to be our ray because we have a starting point, right? That's where the ray starts, and it goes forever in one direction. And if you just want to see like an independent picture of a ray, right, it's kind of like this, right? Again, start at a specific point, and then you continue on forever in one direction. Remember, it's one direction, not both. So here, you're going to the right. And as far as the notation goes, right, you have really similar, right? You have 2 points, so you label this as ray AB. The important thing to know is that the point here, like the point that where the array originates from, is what should go first. So unlike um, the other figures, right, where I told you that the order doesn't matter, right? For example, I said that it could be BA or AB. For array, when you're writing the notation, you have to make sure that it starts at A, right? It starts from that specific point. Like you can't label this as array BA because that would imply that B is the endpoint, right? But in this case, obviously A is the endpoint, right? So again, that's a common mistake. Uh, I kind of see a lot, right? But just make sure that if you're writing the notation down, you start with the endpoint first. And as far as what you should put over the 2 points, it's just going to be an arrow, right? Pointing to the right. That's it. So now let's talk about more like relationships between two figures. And the first kind of relationship we have, it has to do with collinear figures, right? Specifically here, and we will get into collinearity more on in further lessons. Well, let's just talk about collinear points. So first of all, what does collinear even mean, right? It just means if two things are on the same line, right? And collinear points, right, are essentially just two or more points that share the same line, right? They lie on the same line. So for example, you see this visual here, right, with this line and a bunch of points. So I kind of want you to answer this question, right, and just take as long as you need. Um, which of these points would be collinear, right? Which of them lie on the same line? Now, again, right, just by looking at the visual here, you can obviously see that points A, B, and F are lying on the same line. So therefore, points A, B, and F are all collinear, right? Now, points G and H, they're not on the same line, right? So you can't assume that they're collinear, right? Again, right? You can't say A, G, and H are collinear because they don't lie on the same line, right? You have to have a line that goes through the points in order to say that it's collinear. Um, but a really important fact to know, right, for collinearity of points is that any 2 points are always collinear. The if you want to if you want an example that makes more sense, right? Or in other words, right, this just means that if you have 2 points, you can always draw a line between them, right? It doesn't matter how it's oriented, right? So it could be like 2 points here, right? You can always draw a line between 2 points. And that's not the case for 3 points, because if you have 3 points, well, again, right, you need them to be all lined up together for them to be collinear. So, but again, an important thing to know is any 2 points are always going to be collinear. So hopefully that made a bit of sense, right? Again, just think of collinear as things that lie in the same line, right? Now let's go into some other terms you should know. And in my opinion, like this next one, plane, it's not really important to know for this specific course, but again, this is good knowledge to have. So a plane, simply put, is just a flat surface, right? So all these figures that we have learned about so far, right? Lines, line segments, points, arrays, all of these lie on a plane, right? A plane is two-dimensional, and all these figures we learned about at most are 2 dimensions. So essentially, you can put lines, arrays, line segments, points all on the plane, right? You can put all of them on a flat surface, and as you can see with this visual, right, think of this plane as a tabletop, right? And hopefully you get the idea that this is a table, right? Um, but again, right, this is like the flat surface of the table on the top here, and we have one of these figures that we learned about, a line, which lies on this plane. So Again, good knowledge to have, not necessarily uh, something that you have to know, but another term, right? Coplanar. It just literally kind of like similar to collinear. Coplanar just means that two figures lie on the same plane, right? Remember, collinear was that two points lie on the same line. Coplanar means that two figures lie on the same plane. So, for example, here, right? Let's just look at this. If we have a line here, right, and let's say I decide to have another point, like point C, in this case, line AB and point C are going to be coplanar because they lie on the same plane, right? And kind of going back to that 3 point thing, right? Because I said earlier that 2 points are always going to be collinear, right? Now, right, if we have 3 points, 3 points are always going to be coplanar, right? And that means that if you draw 3 points, doesn't matter how you draw them and what orientation, right? It could be in this triangle sort of shape, or it can also be like this. They're always going to share the same plane, and the reason um, is because let's assume that what I'm drawing on right now, right, which is my iPad, right, it's a one plane, right? It's a flat surface, but and it doesn't matter where I draw these three points, right? They're all going to lie on this iPad, right? Because I'm drawing them somewhere in the space here. So again, any set of 3 points are always going to be coplanar. They're going to lie on the same plane. The reason why 4 points are not necessarily coplanar, right, is because you have to think of this in 3D way, right? So if I like draw a 3D plane here with X, Y, Z, right? So you might have 3 points here, which lie on this kind of bottom plane, but you might have like a fourth point which is on top, right? And that's not necessarily on this plane. So the main takeaway is that any 3 points are always coplanar. Next term you should know um, are concurrent lines, and this is just a fancy term for something that's really simple, right? If you have three or more lines passing through a single point, they're concurrent. So for example, you here, right, you see there's three lines, right? One, two, three, and since they all pass through the same point, they're called concurrent lines. Um, Now, do you really have to know this? No. Um, I guess the only application where this would be important is to know that three lines pass through a specific point, right? For example, um, it might be useful to know in some problems that you have multiple lines on a figure, and if you know that multiple lines pass through the same point, then you can like go on from there and make assumptions about how to continue on solving whatever the problem asks you to do. So again, not really useful to know, but just a good knowledge to have. Okay, next up, really important, like extremely important, um, angles, right? Now, the reason angles are really important is because they come up in shapes, right? Like triangles, but also they're important for what we're literally going to do with proofs, right? For sometimes, and again, we haven't gotten to proofs yet. You might have to like prove that two triangles are congruent to each other, and you didn't know that specific angles are congruent to each other or equal to each other. So, but just disregard all of that, right? Simply put, an angle is a geometric figure, and it is formed basically by combining two rays together, but those two rays have to share a common endpoint, right? So if you look at the diagram here, um, right, you have two rays here. You have this ray, all right, ray BA. Remember, right, not AB, it's BA because it starts at B. And then you have ray BC, right? And that's where the two ray definition comes from, right? You have these two rays, and they share a common endpoint, which is B, right? And that is what forms the angle. And that common endpoint, if you want the more geometric, like analog or term to it, it's called the vertex, right? I think you guys have. heard of that before, right? You can think of a vortex as a corner or something, but yeah, right. A vortex is in an angle is just the endpoint that those two combining or those two converging rays share, right? Now the tricky part comes when you're denoting these uh, these angles, right? Now there is a lot of different ways to name this specific angle, right? For example, you can say this is angle ABC, right? And again, if you want to know why that is, you kind of like have to follow this pattern in your head, right? It goes from A to the vertex and then back out, right? So one way you can call this angle is ABC, right? You can also call this angle CBA, right? Because again, you're starting at C, you're going to the vertex, and you're coming back out, right? So CBA, and or you can also just name this angle B, right? And I would actually encourage you not to think of this angle B part, and I'll get to that later because it causes confusion when you're looking at specific figures. But right, just simply put, right, just follow a path in your head when you're naming angles, right? So if you ever look at an angle, start from a specific point, and then just go into the vertex and out the other side, right? Now, I actually do want to go over this before we move on, right? Here you see Um, and actually, this will also explain why I don't recommend you using angle B, right? So in this diagram, right, you see multiple angles, right? Um, for example, angle 1 here, right, is referring to this specific red area, and then angle 2 is referring to this purple area here, right? Now, how would we name angle 1 here, right? I told you to follow a path in your head, right? So we have x, we start at x, we go to y, and then we go to w, right? We come back out at w. So this would be xyw, right? And again, it can also go the other way. Um, but for angle 2, right, follow the same path, right? It starts here, it goes to y, and it goes back out to z. So that would be wyz, right? Now, the reason why I don't want you to say that angle one is called, or sorry, like angle one here is angle y, right? Or angle two here is angle y, right? Is because if you do write down angle y, you don't know if that's referring to angle one or angle two, right? It could be either. So you always want to be as specific as possible when there are multiple angles in a diagram that share like the same ray, right? So again, right, just be as specific as possible when you're naming angles. It clears a lot of confusion, for example, when you're dealing with problems or like when your teachers are checking assignments for you, right? So, really good knowledge to have. That's really important. Okay, next up we have triangles, and I feel like that's the natural continuation after you learn about angles, right? Because if you just look at the name, right, triangle, right, just means three angles. That's how I think of it, right? So it's a shape that contains three angles. And kind of just to show that a bit, right, of course, you can see the picture of the triangle here, ABC, and you have these three angles that I've indicated here in purple. So now, when as far as uh, if you're dealing with like naming angles or naming triangles, it's pretty simple, right? Again, the order doesn't matter. Um, so you can label this as triangle ABC, triangle CAB, CBA, right? So again, when you're writing down the notation for triangles, it doesn't matter what order you put the points in, right? Just make sure you put all the 3 points, right? Now, an important thing to know about a triangle is that it's a figure that's formed by joining three non-collinear points. So the points have to be non-collinear. They can't lie on the same line, right? If you think about it earlier, right, we're talking about these collinear points. If you see these 3 points, right, you can't make a triangle out of three collinear points, right? um, because they lie on the same line, right? In other words, they only have like one specific dimension to it, right? It only goes back and forth, right? It doesn't go up and down if you have three collinear points. So whenever you have a triangle, right, you're essentially joining three non-collinear points together because that third point, right? For example, let's say B was here, right? Just completely disregard the fact that this is even a triangle, right? If B was collinear with points A and C, right, you couldn't form a triangle because this would only have um, this back and forth part, right? Now, the second you take B and you start rising it up, right, it kind of gives it another dimension to it, right? That only happens when that third point is non-collinear, and that's how you form a triangle. So again, all right, a triangle is formed by connecting three non-collinear points, and of course, each point in the triangle, um, points or at least points A, B, C here, they're vertexes, right? Think of them as corners. So that's essentially a triangle, right? Now, next, what I'm going to do is define a triangle in terms of union and intersection, and then I'll explain what those are, right? So you can think of a triangle as the union of three sides, right, that are connected to each other, right? Or like a union of three segments, right? A triangle can be defined as a union of three segments. Now, what does that mean? What does union mean? Well, it essentially means that if you have three segments, right? So for example, here you have segment AB, AC, and then BC, right? If you combine all those together, if you merge them together, you get a triangle. That's essentially all union is, right? You merge three distinct figures together with distinct shapes, and they form a specific overall figure, and in this case, that's going to be a triangle, right? Now, that's different from an intersection because intersection is when you have multiple distinct figures that are sharing a common region or a common figure or a common like location, right? So, for example, right, I think the best example for a intersection in a triangle is if you look at two sides. So if you look at segment AB, and then if you look at segment BC, right, the intersection of those two segments are going to be B, right, because they intersect at point B. So, and just to kind of give another example, right, for union, right, if you have a union of AB and BC, well, what do those two segments form? They form an angle, right? So the union of these two sides here would be angle ABC. So to kind of sum it up, right? In general, you can think of union as the entire figure, right? Or like what you get when you combine and merge all the elements together. And you can think of an intersection as the area or a region that's common um, between the distinct figures that you're given, right? So again, right, it's the area or thing common against amongst figures or sets. And just in case you still don't understand those concepts, right? I think the best way to understand this is with a Venn diagram, right? So let's say you have this Venn diagram, right? And you have these two different sets that contain these natural numbers, right? So set A has numbers 1, 2, 3, 8, 9, 10, and set B has numbers 1, 2, 3, 4, 7, 5, right? Now, what is the union of sets A and B? Well, earlier I told you that the union is the entire concept, right? It's the entire thing. So in this case, the union of these two sets are just going to be all the numbers. So it's going to be 1, 2, 3, 4, and so on and so forth, right? Just including all the numbers that are found in both sets. Now, what is the intersection of both sets going to be? Earlier, I said that the intersection is the common region or like the common thing between two distinct figures, right? or sets. So in this case, the common thing between set A and set B are the numbers in the middle, right? Which are 1, 2, 3, right? Again, if you kind of see this, right, is these numbers here, 1, 2, 3. So the intersection of those two sets are going to be the numbers that are shared between both sets. And in this case, that would be 1, 2, and 3. And that's basically all there is to this first lesson. Um, if you don't understand set and intersection so far, that's completely fine. There's not really a heavily tested topic in this specific course or covered. It's just good knowledge to have, right? So as long as you understand the basic geometric figures, you should be fine for this specific lesson. But I hope you understood all the concepts here. Again, if you have any questions about anything I covered, just leave it down in the comments, and see you next time.